In this video, we are discussing questions on potential divider. The potential divider is a series circuit, that is two resistances connected in series. One resistance, both may be fixed, one may be variable, other one may be LDR or thermistor or any other component. So they share the voltage of the supply. So this is a potential divider circuit. So first part, this question is from May, June 2013, variant 23, and it's question number 6 of that year. So first part, 6A, define potential difference. So what is the potential difference? The conversion of energy from non-electrical to from electrical to non-electrical, because charge gains electrical energy in the battery. Battery gives electrical energy to the charge, electrical potential energy, and when charge passes through the circuit, it uses this energy in passing through the resistance, that is converted into heat if this is a resistance, otherwise any other form of energy like light, etc. So heat and light are non-electrical. So charge gains electrical energy when it passes through the battery. So conversion of energy from electrical to non-electrical. Since it carries only 1 mark, so this 1 point definition will be okay. From electrical to non-electrical, or energy used by charge when it passes from one point to another point. This point is of higher potential, and here it uses the energy, so this point is of lower potential. So battery of force, electromotive force 20 volt and 0 internal resistance is connected in series with two resistors R1 and R2 as shown. So this is a potential divider circuit. The resistance of R2 is 600 ohms and the resistance of R1 is varied. It's a variable resistance, so it can be 0 and it can vary from 0 onwards up to maximum 400 volts, 400 ohms, sorry. So the maximum potential difference across R2 is to be worked out. So what we will do to calculate the maximum potential difference across R2, see it's a potential divider circuit and potential difference 20 volt EMF of the battery is shared between R1 and R2. So the one which has greater resistance, it will be using up, the charge will be using up more energy while passing through that resistance. So if R1 potential difference across R2 has to be maximum, maximum means 20 volt. So for that purpose, R1 should be 0. It is a variable resistance, so it can be adjusted to 0 onwards up to 400. So when R1 is 0, the charge will use no energy while passing through R2, R1. So when R1 is 0 ohm means the PD across R2 will be maximum. PD across R2 charge will use entire 20 volts across R2. So across R2 will be 20 volt. When R1 is at any other value rather than 0, then part of the voltage EMF of the battery will be shared by R1 and R2. Now minimum potential difference. So minimum potential difference means the voltage has to be used, the charge should use energy while passing through R1 as well. When it was at 0, there was no energy used by charge while passing through R1. But when R1 has some value more than 0 ohm, so charge will be using that energy. So for the potential difference across R2 To be minimum means R1 should be at the maximum resistance, because when series circuit the current is same. In series circuit the current is same, and R2 has the value 600 ohms. What is R2? 600 ohms. And it, when R1 was 0, entire 20 volts were across R2. But when R1 is at 400, the maximum resistance, the charge will use energy while passing through R1. So what will be the potential difference? Here we will use potential divider formula. What is the potential? Because we have to calculate the potential difference across R2. So we will say that is the V2. PD across R2, we say V2. Current is same. So the greater the resistance, the greater will be the potential difference across the resistance. We have called it V2. V2 will be equal to R2. This is the formula of potential divider over R1 plus R2 into V input. V input is 20. So when we solve it, 600 divided by 400 plus 600 is 1000 into 20. So this cancelled, these two zeros, these two zeros. So 6 to the 12 volt. We can simply apply Ohm's law also. First, we have to find out the current. I is equal to V total, that is EMF of the battery, over R total. Means V total is 20 and R total is 1000. This is how we will get the current. Current will be 0.02 ampere. So what is V2? V2 is IR2 I 0.02 into R2 is 600. So again the answer is 12 volt. So you should remember, when I is constant in series circuit, same current flows through the battery R1 and R2. So the PD will be directly proportional to R. The greater R, the greater will be the potential difference across that. Since R2 is greater resistance, so it is the charge uses 12 joule of energy. 12 volt means 12 joule per coulomb. Every coulomb of charge uses 12 joule of energy while passing through R2. So where will be the rest of the energy used? While passing through R1. How much? 20 minus 12, that is 8 volt. PD across, though it's not asked, but here just I have wanted to clarify, potential difference across R1 will be 8 volt. And when the R1 was set at 0, there was no potential difference across R1. So this part is done. Now let us see next part. Now there are some changes made in the circuit. A light dependent resistor, that is LDR, is connected in parallel with R2. So R2 is 600 and R1 is adjustable, and LDR's resistance is not here mentioned in this part. Let us see what the next part of the question says. When the light intensity is varied, because LDR, light dependent resistance, the greater the intensity of the light, the minimum will be the resistance. And when LDR is in darkness, the resistance will be more. So here, when light intensity is varied, the resistance of LDR changes from 5 kilo ohm to 1.5, 1.2 kilo ohm. So here for maximum intensity, calculate the total resistance of R2 and LDR. R2 and LDR in parallel. So for maximum intensity, for maximum intensity of light, the resistance of LDR will be 1.2 kilo ohm, that is 1200 ohm. LDR 1200 ohms for maximum intensity. For minimum intensity of light, it will be 5 kilo ohm. And R2 is 600. So what will be the total resistance? So we can apply the formula of resistances in parallel. R total will be equal to 1 upon 1200 plus 1 upon 600 bracket minus 1. Otherwise, if I don't put minus 1 in bracket, I will have to use 1 upon RT. So when we solve it, what will be the answer? 1 plus 2 over 1200 minus 1. When I reverse it, 1200 over 3. The answer is 400. Total resistance, there this is a parallel combination, the resistance decreases. It will be smaller than the smallest resistance. The R2 is 600, R1 LDR, which is in parallel to R2, has 1200 ohm resistance. So total, the parallel combination has resistance 400 ohm. So this is our answer, 400 ohm. Now the resistance of R1 is varied from 0 to 400 ohm in the circuit of figure 6.1 and in figure 6.2. Figure 6.1 has no LDR connected in it, but figure 6.2 has LDR connected. State and explain the difference, if any, between the minimum potential difference across R2 in each circuit. So in second circuit, the total resistance with LDR is 400 ohms when the light intensity is maximum. And so potential let us calculate what will happen, though no numerical values are required. So you don't need to put the values, but here I will explain with the help of some values. In the first part, what was the minimum potential difference across R2? If you remember, that was 12 volt. Okay, minimum potential difference across R2 was 12 volt in figure 6.1 when no LDR was connected. And in the second case, what will be the potential difference? If you see the figure here, total resistance of this combination is 400. And for minimum potential difference, R1 should also be at maximum value. The R1 value of R1 should be 400. Okay, so then the potential difference will be minimum. And the total resistance of this combination, I may label it A, B, and C. So AB is 400 ohm and combination resistance between BC is also 400. We just calculated. RBC is also 400 ohm. So they are equal in value. It means the potential difference across R1 and R2 will be shared equally because this is also 400 V1 and V2 is also 400. This is 10 volt, half, total resistance is 400, this is total 400. So voltage will be shared equally, half of 20 is 10 volt. 10 volt and 10 volt. But in the first case, when LDR was not connected, the minimum potential difference was found to be 12 volt. Which means potential difference has decreased. In first case, in the absence of LDR, the minimum potential difference across R2 was 12 volt. And in the second case, when LDR is connected in parallel and the light intensity is maximum, so resistance is minimum, and the parallel combination of LDR and R2 have resistance 400. R1 is also 400. So minimum potential difference is now 10 volts. So it is less than before. Okay, so what we will write here, the potential difference across R1 in the first case is figure 6.1. V2 was 12 volt. In figure 6.2, V2 is less because total resistance has decreased and V is proportional to R. First, the total resistance of R2 was 600, but now it is 400. So in this case, V2 is 10 volt. So what do we say? The potential difference across R2 in each case when we compare PD decreases. Now next question, it's also related to potential divider. It is from October-November 2010, variant 22. A levels 9702. The variation with temperature of the resistance RT of thermistor is shown in figure. So on y-axis, the resistance of thermistor is given in kilo ohm and the temperature is taken on x-axis. So the temperature, minimum temperature is 0. Temperature varies from 0 to 25 degrees Celsius, and the resistance at 0 degrees Celsius is 3 and 4, 3.5 kilo ohm, 3500 ohms. Let us see what is asked in the question. There is a circuit which is given here, and the resistance of LD thermistor and the temperature is plotted in the previous figure. The thermistor is connected into the circuit of figure 6.2 and it is in parallel to 1.6 kilo ohm resistor. And this combination is in series with 1.2 kilo ohm resistor. So this is a parallel combination between A and B, and voltmeter is also connected. The battery is of EMF 9 volt and negligible. Again, the previous question also had no internal resistance in the battery. It means no lost volt. Okay. The voltmeter has infinite resistance. When voltmeter has infinite resistance means no current will pass through voltmeter. It will measure the potential difference between the points A and B. It will not draw any current, or the current which it will draw, that will be ignorable. So for the resistance thermistor at 25.5 degrees Celsius, calculate the total resistance between A and B. When the temperature is 22.5 degrees Celsius, what will be the resistance? We will check it from the graph. I've copied the graph again, and I've located the values also at 22.5 degrees Celsius. The red line shows that temperature 22.5 and the resistance is 1.6 kilo ohm. It means 1600 ohm. So this is what we had to write. What is the resistance across the resistance of this thermistor? 1600 ohms, and we have to calculate the total resistance between the 2 points. So what will be the total resistance? The resistance which is connected in parallel to thermistor is also 1600, and two 1600 ohms resistors, when they are in parallel, the total resistance will be half. The easy way is what? Number of total resistance, one resistance divided by number of resistance, or you can apply the formula. R total is equal to 1 upon 1600 plus 1 upon 1600. You have studied in O levels also, when two identical are in parallel, resistance will be half. So this will be 2 over 1600 minus 1. So 800 ohm is the combined resistance between A and B. The reading on voltmeter, what will voltmeter show? For that purpose, we have to take the resistance. V2 is equal to R2 over R1 plus R2 into V input is 9 volt. So here R2 800, R1 is 1200, 1.2 kilo ohm means 1200, and this is 800 into 9. So when we solve the question, the answer turns out to be 3.6. This is 800 over 2000 into 9. So these two zeros cancelled, and this is 0.4 into 9, that is 3.6 volt. The potential difference across the combination of thermistor and the resistor connected in parallel is 3.6 volt. This was 3.6 volt. Now what next part says, the temperature of the thermistor is changed. The voltmeter now reads 4 volt. This voltmeter, it reads the potential difference between A and B. It reads 4 volt. It means remaining volts out of 4, out of 9, 4 are across AB. So 5 volt will be across this resistor. So you have to calculate the total resistance between A and B. So we can, how can we calculate? There are a number of ways. Either we find out the current, and how can we find out the current? We know the potential difference across 1.2 kilo ohm is 5. This is 5. 9 minus 4 is 5. This has 4. This voltmeter, it shows 4 volt. So we can find out the current using the formula I is equal to V over R 5 volt over 1200. So this is the current 5 over 1200, and same current will be total same current, though it will be dividing between the two paths. The total current will be the same 5 over 1200. So we can calculate uh, this resistance. We know resistance is proportional to the voltage. So 4 over our total between, what is 4? We can apply this voltage and resistance ratio, V1 over R1 equals to V2 over R2. So suppose this is V1, 1.6 kilo ohm, and a thermistor in parallel. The total resistance is RT and potential difference is 4 volt. This potential difference is 4 volt and this is R total equal to 5. Current is same. What is current through this part? 4 over R total. Potential difference across the total resistance. What is the current through this? 500 over 1200. So if we make RT subject, this will be 1200 into 4 over 5. Cross multiplication gives us the value. So this will be 960 ohm. When I solve it, this will be 960 ohm. What is the other method? We can apply the formula of potential divider. That is also we can solve this question, but this is sufficient. This is enough. We can apply the voltage to resistance ratio. V1, V4 volt. I have taken this here as V1 and this I have taken as V2. So this is R2 and this is R1. The parallel combination is R1, or this is, you may call it R total between this two. So this resistance is 960. 4 over R total, I1, I through 1.2, or total current through 1.6 and thermistor will be the same. So 5 over 1200. 1200, this one, 4 over R total. So I made R total subject and worked out the value of combined resistance. This is the combined resistance of this. Combined resistance of this is 960. Okay, between A and B. RAB you may call it 960 ohm. Let us see what next part says. We have to remember the value of combined resistance 960 ohms. The temperature of the thermistor. So that 960 ohm was the resistance of parallel combination. It was not the resistance of thermistor. So first we have to find out the resistance of thermistor so that we can find out the temperature using this. So here I will apply the formula of parallel combination of the resistor. This is 960. So 1 upon R total is equal to 1 upon R1 plus 1 upon R thermistor. This is 1 upon 960 is equal to 1 over R1. R1 was 1.6 kilo ohm. So 1600 plus 1 upon R thermistor. So what will be 1 upon R thermistor? I will take it to the other side. 1 upon R thermistor is equal to 1 over 960 minus 1 over 1600. So this turns out to be, if I take the reciprocal, R thermistor is equal to 1 over 960 minus 1 over 1600 minus 1. So if I solve it separately, 1 upon 960 and 1 upon 1600. The answer, and take the reciprocal of the answer. The answer will be 2400 ohm. So at 2400 ohm, let us see what is the temperature from the graph. So resistance of thermistor is 2400 ohms. Let us see the temperature. I've already marked the values. Uh, 24, and this is 2 kilo ohm, and this is 3 kilo ohm. So 2.1, 2.2, 2.3, 2.4 kilo ohm means 2400 ohm, and this is 11 degrees Celsius. So the temperature of thermistor is 11 degree Celsius. This is 11. Why it was of 2 mark? It was not only matter of locating the value, it was the matter of calculating the resistance of thermistor as well. Okay, now a student suggests that the voltmeter reading up to 10 volt could be calibrated to measure the temperature. Calibration, finding out unknown value with the help of known value. So just two advantages of using the circuit in figure 6.2 with this voltmeter for the measurement of temperature ranging from 0 degrees Celsius to 25 degrees Celsius. We have to first see the circuit. This is the circuit. Using this circuit, what will be the will this voltmeter be suitable or not? Okay, so let us see the graph once again. What was the maximum temperature? 25 degrees Celsius. And at 0 degrees Celsius, what is the resistance? 3.5 kilo ohm means 35. So what will be the voltmeter reading? Is this graph linear? First you tell me. No, it is not linear. Okay, it means the resistance of LDR does not change linearly with the temperature. The decrease in resistance with the rise in temperature is non-uniform. And since the potential difference is proportional to the resistance, so potential difference changes in the potential difference with change in the temperature will also be non-uniform. So first point, the graph, the voltmeter reading, which will the thermometer which we will calibrate will be non-linear. The first reason. Okay, let me show you the range of the voltage. It shows the at 0 degrees Celsius, what will be the voltmeter reading when the temperature is 0 degrees Celsius? What is the resistance of LDR? 3500, and it is in connected in parallel to the 1600. So if I solve this, though it's not needed to solve, but I'm just solving V across the thermistor and parallel resistance. 3500 kilo ohm is the resistance. Uh, First, let me find out the total resistance of the combination. So for the total resistance of the combination, I'm using famous parallel formula of two resistances in parallel. So R1 into R2 upon R1 plus R2. So 3500 into 1600 over 3500 plus 1600. In this case, you don't need to take the reciprocal because we have used R1 into R2 when two are in parallel divided by R1 plus R2. So the answer is 1100 ohm. The combined resistance, of course, will be smaller than the smallest resistance. That is 1600 is the smallest one. The combined effect is 1600 ohms. Sorry, combined effect is 1100 ohm. And when we find out the voltage across this, what will be the potential difference across this? V will be equal to 1100 over what was connected in series with that 1200. 1100 was in series with 1200. 1100 combined effect of thermistor and the resistor which was in parallel to it. 1100 battery's voltage 9 volt. So when we solve it, the answer turns out to be around 4 point something, that is 4.3 volt. So this will be the maximum voltage the voltmeter can show, 4.3 volt when the resistance of the thermistor is 0 degrees Celsius. So we have to remember the value here. And let me go to the question. See, so only a small part of the scale is used because the potential difference, what was the potential difference for 2.2? We just calculated it for the value of 2.2, 22.5 degrees Celsius. So 25 degrees Celsius, what will be the voltage? What will be the resistance? If we extend the graph, that will be around 1.5. Means the voltmeter reading will be around. In the first case, the what was the voltmeter reading when the resistance of thermistor was um, 12, 22 point, sorry, what was the resistance? 1600. At this resistance, 22.5 is the temperature and 1600 is the resistance. So resistance will be slightly greater, 1 point slightly smaller. When I extend the graph, so it may be around 1.5 kilo ohm. So when we solve that value of voltage shown by the voltmeter, this was 3.6. This was, if you remember, this was 3.6 volts, so it will be slightly less. So voltage variation is from, you can say, 3.5 onward to 4.3. So it means only a small portion will be used of the voltmeter, ranging from 0 to 10 volt. Only voltage will vary from 3 point something to 4 point something. So here only a small part of the scale is used, and since it means this will not be very sensitive because the uh, markings will be very close to each other. Divisions of the voltmeter will be close to it. This is a diagram of a calibrated voltmeter which shows the temperature here. So since our voltage lies between 3 and 4, so this may be the suitable one. You can see the separation between the two divisions is not uniform. So non-linear scale, one thing. And second thing, only small portion is used. Only this. So the divisions, it means the points will be very close to each other. It means it will not be that sensitive to measure the minor changes in the temperature. Okay, small portion of the graph is used and graph is non-linear and it's not a straight line. Okay, so all the graphs here, they show a non-linear relationship. You can see V here the end is the separation in the beginning is more and separation at the end is smaller. Here separation in the small beginning is less and later on it's more. So these all are non-linear graphs. So our graph may be of this shape where 3 and 4 volts are lying. So at 3 point something temperature will be 25 degrees Celsius, and at 0 degrees Celsius the voltmeter reading will be around 4 point something, as we calculated that was 4.3. So this may be the suitable thing, and a small portion of the graph is used. So read this again. A linear graph is a straight line graph. So they don't depend linearly on each other. Means change in voltage, change in potential difference with the changes in temperature is non-uniform. Okay, similarly, the voltage would correspond to different range of the temperature at different region of the temperature. Some points the divisions will be closer and at some point they will be away from each other. The separation of the scale would be small in one region and the large in at another region, like these are shown here. Okay, so the graph is going to be non-linear and the graph is not like it's showing less sensitivity. We can't note down the minor changes in the temperature because the points are very close to each other. Now the next question, it is 9702 22 May June 2014. And here, this is again a potential divider and 24-volt battery is given in the circuit. Two resistors, X and Y are in series and X is in parallel to a variable resistor. So resistance of X is constant. It is fixed resistor. The resistance of Y is 600, 6 ohms. This is also constant. The battery has EMF 24 volt and zero internal resistance. Again, there will be no energy lost by the charge while passing through the cell. Variable resistance R is connected in parallel with X. And the circuit, the current I from the battery is changed by varying this. When we increase the resistance R, the total resistance between A and B will increase, and so will be the total resistance between A and C. What does that mean? If R increases, this R, I mean this R, if this R increases, RAB will increase, parallel combination increases, and so will our AC. Total resistance will also, this is fixed, but this is varying due to this variable resistance. So our AC will also increase. So current decreases when R is increased. And if R is decreased, the total resistance will decrease and our current will increase. So current I from the battery is changed by varying R from 5 ohm to 20 ohm. Okay, so the minimum resistance of this variable resistance is 5 and maximum is 20. The variation of R or variation with R in of I is shown. So I and R. Here, what is R? The variable resistance. When variable resistance is 5, the current is maximum, and we will see that slightly above 2.5 ampere. And this decreases non-linearly with the change in resistance. Explain why the potential difference between A and C is 24 volt for all the values of R. Whatever is the value of R, the potential difference between C will remain same because the charge uses no energy while passing through the cell. There are no lost volt because battery has no internal resistance. Okay. So what we will write? No internal resistance. So no lost volt. Used figure 6.2, that is graph and state and explain variation of the potential difference across Y as R is increased. Numerical values are not required. So here we have to write, first we have to study the relationship between what? Potential difference across Y as R is increased. Here Y is this. Okay, when R is increased, what will happen? The total resistance between A and B will also increase, and current will decrease. Since Y is fixed 6 ohms, so whatever is the current, potential difference across Y will be 6 into I. And since I decreases due to increase in R, the potential difference across Y decreases. R increases, RAB also increases. What will happen to I? It will decrease. And PD across LDR depends upon this I. PD across Y, current is same through both of them. Across Y is I into V into I into R. I into R. I is to be calculated for different values, so I'm not calculating, into 6. So 6 ohms. 6 into I is decreasing, so V across Y will also decrease. Vy will decrease. Now for R for 6 ohms, when R is adjusted at 6 ohm, what do we have to do? Let us see. Show that the potential difference between A and B is 9.6 volt. Potential difference between A and B. A and B means these two. Between X and R. They are in parallel. They have the same potential difference. Okay, that is 9.6 volt. So we can locate what is because the graph is plotted between the variable resistance and the current. And here I have taken the other graph, and for 6 ohm of R, the current is 2.4 ampere. So when the current is same, the total, this is the total current. The graph is plotted for the current I. Which current? The total current. This is total current. Okay, that will be dividing here in this between in a path AB. It will be dividing between X and R, but the total current is 2.4 ampere. So we can find out first the potential difference across Y, because this is easy step, and then we can calculate the resistance of X. So PD across Y is Vy is I into R, 2.4 into 6. So this is 14.4 volt. So what will be the potential difference between that AB? VAB will be 24 minus 14.4, because that was the potential difference across other resistance, VY. So this across the parallel combination VAB, it is 9.6 volt. Potential difference will be the same across the parallel combination. X and R both will have potential difference 9.6 because they are in parallel. So what will be X? We may check it. That is V R total. R total is 9 point V over I. Total voltage between A and B is 9.6, and total current is 2.4. So this method is going to be a little bit lengthy, because total combined resistance, then we will have to apply the formula of parallel combination. Anyhow, we can have the other way also. 9.6 is the voltage. We can get the voltage of resistance of the parallel combination by applying formula of total voltage over total current. This is how we can also calculate the total resistance. This R total is for that parallel combination, but that will need one more step. So I am going to take you to the easy step. R total 24 and the current is 2.4. So this is 24 over 2.4 gives us 10 ohm. Total resistance of that circuit, including all the resistance, is 10 ohms. And out of 10, the Ry is 6. Ry is 6. So what is Rx? Rx will be, Rab will be 10 minus 6. 10 is the total resistance of the whole circuit, and 6 is the resistance of Y, so 4 ohm. The total resistance of the parallel combination is 4 ohm. Now 1 upon R AB, that is why it is of 3 marks. It needs number of steps. R AB is equal to 1 upon X plus 1 upon R. What is R total? 1 upon 4. 1 upon is equal to is equal to 1 upon X plus 1 upon 6. So 1 upon X is equal to 1 upon 4 minus 1 upon 6. So when we solve this, X turns out to be 12 ohms. So resistance of X, you will have to take the LCM. Let me do it for you. 12 and 4 3s are 12. 6 2s are 12. Okay, so 3 minus 2, and then at the end we have to take the reciprocal. So that is 12 ohms. Now calculate the power provided by the battery. So power's formula is V into I. Rx is 12 ohm, and what is the power? Power is V into I. Current is 2.4. So we will use the easy formula. P is equal to V into I. V 24, and battery is drawing the current 2.4 ampere. So 24 into 2.4, that is 57.6 watt. If you want to express your answer in two significant figure, this will be 58 watt. Okay. The next part, state and explain qualitatively how the power provided by the battery changes as the resistance R is increased. When R is increased, you know the total resistance will increase. R increases. R total increases. R is the variable resistance. So that will cause increase in the total resistance. I will decrease. When I decreases, you can see the formula V into I. 24, and at smaller current, the power will decrease. You can see, because EMF is not going to change, that is still 24 volt. And you can use this combination also. R power is equal to V square over R. Using this combination also, you can say the answer. V is same, R has increased. When the denominator increases, power will decrease. So what will you write here? The power decreases. R increases. R total, yeah, that is R AC increases. I decreases. P is equal to VI decreases as EMF is same. So that's all. We have discussed three questions related to the use of potential divider circuit. So that's all, and Allah Hafiz.